Welcome everyone to this lecture on the theory and intuition behind hierarchical clustering. Like most clustering algorithms, hierarchical clustering simply relies on measuring which data points are most similar to other data points, and data points that are similar to each other are then going to get grouped in the same cluster, where similarity is defined by choosing a distance metric. This should feel really similar to other clustering methods, such as k-means clustering. So why would we use hierarchical clustering versus other methods? Well, there's a bunch of pros to consider. One is that it's easy to understand and visualize, and it can also help users decide how many clusters to actually choose. You don't necessarily need to choose the number of clusters beforehand, which is very useful compared to other clustering methods like k-means clustering, where you had to know how many clusters you wanted to find before actually running the algorithm. And the visualization of the hierarchy structure is what helps the user decide. So, how does this actually work? Well, hierarchical clustering is essentially going to divide all the data points into every single potential cluster, and it's going to visualize it in a way that is going to be clear to the user where a reasonable stopping point is. It can also then kind of suggest how many clusters you should be looking into. The first is the agglomerative approach, where each individual point begins as its own cluster, and then clusters are joined together. There's also the divisive approach, which is essentially the opposite. All points belong, at first, in the same cluster, and then clusters are split based on how different they are. Again, using a similarity metric, but instead of minimizing it, you're maximizing it. So let's talk about agglomerative clustering, which is the most common way to perform hierarchical clustering, where we're going to divide points into potential clusters. Specifically, what we end up doing is at the very start, if we were to have 6 unique points here, n1, n2, n3, n4, n5, and so on, what we want to do is cluster these into similar looking groups. So based off the features of these points, we calculate the similarity based off some sort of distance metric. And then we decide what are the two most similar points in these clusters. So essentially, n1 is most similar to n2, and then n3 is most similar to n4, n5 is most similar to n6, and so on. Obviously, I have it very convenient here, where n1 is most similar to n2, but we could rearrange the x-axis if we happen to find n1 is most similar to n3. So here are our clusters, and this is the agglomerative approach, where technically each point started as its own cluster of 1, and now we have clusters of 2. And then what we begin to do is slowly find which clusters are most similar to other clusters until we get something that looks like this, a hierarchy tree, otherwise known as a dendrogram. Now, opposite of the agglomerative approach is the divisive approach, which starts with all points belonging to the same cluster and then begins divisions to separate out clusters, essentially the reverse of what we just did. Now, for the hierarchical clustering process, mathematically speaking, it's actually quite simple. All we're doing is we're going to compare data points to find the most similar data points to each other. Then we simply merge those to create a cluster. Then, now that we have clusters, we compare clusters to find the most similar clusters and merge those again. And we keep repeating this until all points belong to a single cluster. And we're going to keep track of each of these steps in order to create that tree, showing all the potential clusters. So for example, here we have the MPG dataset, or miles per gallon dataset, where we have a bunch of features for a bunch of cars. And what we could do is slowly figure out what car is most similar to another car in the dataset and merge those into a cluster, then figure out, well, what cluster of 2 cars is most similar to the other cluster of 2 cars, and keep merging it until you get something that looks like this on the left-hand side, which is Seaborn's cluster mapping. So how does this actually work, this dendrogram that we're seeing on the left-hand side? Well, there's still a few key topics we need to understand for hierarchical clustering. The first one is the similarity metric and what options we have there. Second is the dendrogram, which is the visualization we just built out. And then third is the linkage matrix, which is actually the mathematical matrix used to build out the dendrogram. When we're thinking about similarity metric, just like in k-means clustering, it's simply measuring the distance between 2 points, and there's lots of different ways to do this. There's Euclidean distance, Manhattan distance, cosine distance, and many more options. By default, we'll use the Euclidean distance, and it's actually quite a good choice. So why is Euclidean distance a great default choice? Well, the first part that makes it so great is that it's pretty easy to understand. And if you've taken a basic geometry class, you'll remember the Pythagorean theorem, which is to say a squared plus b squared is equal to c squared. That's what Euclidean distance is. It just generalizes this to n number of dimensions, or n number of features. So for example, what we have here is we're saying what's the distance between point P and point Q. And you can see this is essentially just the triangle being constructed out, that we can say a squared plus b squared is equal to c squared. That is to say q1 minus p1 squared plus q2 minus p2 squared is equal to dp of q squared, that is the distance squared. So you could just take the square root of both sides, and then given your understanding of q1, p1, q2, and p2, which in our examples will just be feature values, we could easily calculate the distance between these 2 points. So not only is it easy to understand, but it's also going to be very convenient for scaled data. If we're thinking about the Euclidean similarity metric or Euclidean distance, each dimension would be a feature corresponding to our data set, which means for n data points and p features, we would eventually calculate something that looks like this, where I would say the distance squared is equal to, and for 2 particular points comparing, n is equal to 1 versus n is equal to 2, I would simply go through p features and then start subtracting the differences for feature 1, for example, between the 2 points, square it, plus, and continue this all the way to p features. Now let's imagine I used a min-max scalar. That means I could scale all the features to be between 0 and 1, which would allow me to quickly figure out that the maximum distance between a feature would be 1, because I could have at most a value of 1 and at least a value of 0, so 1 minus 0 squared would then be 1 squared, which is 1. And you're going to see that pop up when we actually code this out later on. So just to plant the seed in your mind, using Euclidean similarity metric along with a min-max scalar leads to some very convenient math later down the line. So just keep that in mind for later on. Okay, now let's talk about the dendrogram. This is going to be a plot displaying all the potential clusters. Now the downside here is that it's very computationally expensive to compute and display for larger data sets, but it is very useful for deciding on the number of clusters. So that's your trade-off. What it looks like is something like this. Here we can see a dendrogram for the 6 data points, n1, n2, n3, and so on. But there's a couple more things we want to display on this axis. You'll notice that the y-axis actually has different lengths for what we're going to call these link points. And what's actually happening here is the y-axis is going to be a representation of the distance between the clusters, or the distance between the points. So literally what we're saying here is, for example, n3 and n4 are actually very similar to each other because it's a very short distance up the y-axis before we begin to join those together. Versus something like the cluster of n5 and n6 is not so similar to the cluster that contains all 4, n1, n2, n3, and n4. So that's the difference between this kind of short little links that don't go too far into the y-axis versus something really long. It basically says that you have a very large distance between this particular cluster of n5 and 6 versus the cluster of those 4. Now what's also really nice about the dendrogram, which is kind of the key to hierarchical clustering, is that you could technically use some sort of slice to decide your cluster count. For example, just visually what I could do is, if I were to slice this visualization up here at the very top on these 2 links, then I would have created 2 clusters. And then I could decide that my number of clusters is equal to 2. And here we're deciding this based off how long those links are in the y-axis. Or what I could do is do the slice further down the line. And here, if I slice, I'm going to end up with 3 different clusters. And you can imagine, for a real data set, I could use this in order to figure out what is a reasonable place to actually kind of cut off this hierarchy where those distances along the y-axis are no longer changing so dramatically. Now the last thing I want to discuss are the linkage, which is an idea that essentially answers 2 questions. How do we measure the distance from a point to an entire cluster? And how do we measure distance from a cluster to another cluster? So once 2 or more points are together and we want to continue the agglomerative clustering to join 2 clusters together, we need to decide on a linkage parameter. Let me just quickly visualize this for a feature set of two features, x1 and x2. Here, I've already done a little bit of clustering, but now it's time to move further up the hierarchy and decide whether or not these two clusters should be joined together and what metric should I use. I already know my distance metric, for example, Euclidean distance, but when I already have two existing clusters, I need to actually decide how or where do I measure this distance from. Should I measure it from the two closest points on each cluster? Should I measure it from the two farthest points on each cluster? Maybe I should be try to do some sort of reasonable compromise and say I'm going to take the center of each cluster and measure the distance between the centers of these clusters. Or maybe I'm just going to try to minimize the variance of the points within a cluster. So linkage, formally speaking, is the criterion in determining which distance to use between sets of observation. And the algorithm will merge pairs of clusters that minimizes that criterion. So there's a bunch of different linkage parameters you can use. There is the Ward linkage, which minimizes the variance of clusters being merged. There is the average linkage, which uses the average distances between two sets or two clusters. And then you also have minimum or maximum distances between all observations of the two sets. And these are hyperparameters you can easily swap in and out in scikit-learn. Let's go ahead and move on to exploring these concepts directly through code. Everything we just talked about here, the dendrogram, linkage matrix, and then actually deciding on the number of cluster counts is going to be detailed when we actually jump into the code. So try to keep these points in mind when we go to the next lecture. I'll see you there.